impact modeling of functional graded materials using state-based peridynamics. Yes, Adem.
Thank you, Professor. Hello everyone, my name is Adem Candaş. I'm a mechanical engineer and I'm working as a lecturer in Istanbul Technical University, Faculty of Mechanical Engineering. And I will present my research on impact modeling of functional graded materials using state-based peridynamics. And our primary motivation is to understand the behavior of the functional graded materials under impact loading. And to do this, we develop a model to simulate the crack propagation in FGMs. And we used a rectangular body from the Kalthoff-Winkler experiment, maybe you know that. And in that experiment, a load is applied to a plate, a three-dimensional plate, and we track the crack tip to determine the crack velocity. And we used ordinary state-based peridynamics. The professor can introduce us the types of the peridynamics, you know that. And this is the very fundamental equation of the motion, equation of the peridynamics, the equation of the motion. The theory uses the integral equations that can be applied to any kind of discontinuity, such as cracks. That is why we use the peridynamics in the crack modeling easily. And this is the discretized form of the equation of motion. And you see that there are some, sorry, that's a pointer here. We have the material points X here and its family members X prime here, and there are some kind of connection between them. We call them as bonds. X prime is the family member of the material point inside the horizon of the material point X. And U is the displacement vector, and B is the body load, or rho is the mass density in this formula. And the force T is the force vector that the material point X prime exerts on the particle X, and the T prime is the opposite force coming from the X to the X prime. In bond-based PD, the T and the T prime are equal in magnitude and they are parallel. And in ordinary state-based PD, the forces are still parallel, but they don't have to be equal. Their values can be different between them. And in the third kind of peridynamics, the non-ordinary state-based PD, they don't have to be parallel in direction. And the formulation of the bond forces and the stretch are given here. When the stretch between two material points is greater than a critical value, we call it is critical stretch value, the bond breakage occurs. And as you see in the figure, the breaking of the bond between two material points is related with the bond stretch, and the breaking means the eliminating of their interaction. They cannot get in touch with anymore after the bond breaking. And this is how the PD defines the damage. And to define a broken bond, we used a history-dependent scalar valued function, step function. Its value is 1 when there is a healthy bond between two material points, and it's 0 when the bond is broken. And the critical stretch is formulated with the fracture energy release rate and bulk modulus, shear modulus. Sorry.
Failure in peridynamics.
Yes.
Seems that you are describing that peridynamics is not good. You should write this modeling failure using peridynamics. Yeah. Otherwise, one looks at, okay, you are telling that your peridynamics is completely wrong. because
interesting.
these aspects are important.
Yes.
I was wondering. Sorry, just.
No, it's okay. Yes, it's interesting. So, and this figure shows the broken bonds of a material point in a horizon, and the point A here has lost its connection with its family members on the right side of the orange line. The orange line is the crack line, and you see that the crack line is very close to the material point A, and the damage level for material point A is about 40%. And we have another points just below the material point A, the point B, and this point B is affected by this crack line. Some of the bonds of the B are broken because of this crack line. You can see the blue dashed line here because of they are cracked because of this crack line, and the damage level for the material point B is about 11%. And you can easily define a crack or predefined cracks or any kind of macro and micro cracks in peridynamics easily because of these concepts. Just you need to eliminate between the bonds just through the going through the crack lines. And this is the local damage formulation, and it means that the proportion of the number of material points, broken material points, to the number of bonds, total number of bonds for a single point. In this example, it's A or B. This is the geometrical definition of our model. In Kautov-Winkler experiment, there is a rectangular body. This is the half of the body, and it's symmetrical on this axis, on the right axis. I just draw the half of it. And during simulations, the structure is assumed to be traction-free and at rest. And we also assume the projectile as a rigid body. It's coming from the top of this side. And we applied a constant velocity to do this projectile. It's about 32 meters per second. And we discretized the body with 201 and 101 and 9 material points along X, Y, and Z axis. And the total number of material points is about 1,800. And the horizon radius is 3 times of delta. Most of the studies use this value. And you see the time step. And in the figure, you can see the graduation effect on the material points through the vertical axis because we tried to model the functionally graded materials. And the red small lines, these red small lines are the micro cracks just located around the macro cracks tip to get a toughening effect and accelerate the crack propagation. And these are our previous works. The same impact loading is applied in both models. And at the left side, you see the crack propagation in homogeneous material model. And there are some micro cracks located around the macro crack tip to obtain the toughening effect. And these micro cracks accelerate the crack propagation as around 10%. And when we apply the functional graded material model in the same model, we got 13% deceleration in velocity. And both of them are bond-based PD, and in 3-dimensional structures, the Poisson ratio is limited to 0.25 in the Poisson ratio. If you want to use another Poisson ratio, you need to use the ordinary state based or non-ordinary based PD. That's why we use this study to see the effect of the Poisson ratio in the crack propagation. We need to use the ordinary state based peridynamics. And we have 7 cases to see the effect of the changing of the material properties. And Young modulus, fracture toughness, and the mass density are increasing from the minimum values at y0 to the maximum values at y 0.1 for case 2 and case 4 and case 6. And on the other hand, the cases 3, 5 and 7, the values are decreasing from top to the bottom. And case 2, 4 and 6 they can be considered as a mirror image of the 3, 5 and 7 on the horizontal middle axis. And Poisson's ratio is constant for from 1 to 5, and we can observe the gradation effect of the Poisson ratio on the 6 and 7 cases. These are our first 3 cases. The correct propagations of the cases 1, 2, 3. I present you the moment at the 91 microsecond and 104 microseconds to snapshot of from the results. You see the damage scale that varies between 0 to 1 below, and the complete fracture occurs at 95 microseconds and 100 microseconds for case 2 and case 3, but it's a little bit longer in the case 1. Case 1 is the homogeneous material model, as I said, and case 2, the material properties are high at the top and low at the bottom. At the case 3, it's opposite of the case 2. And when comparing the case 1 and 2, the average velocity values here a little bit increase. However, the velocity is significantly lower in the case 3 when you change the direction of the gradation of the material properties. This difference means that the direction of material gradation plays an important role in the toughening mechanism. It's very effective, very important to crack propagation velocity. And okay, case 4 and case 5 are the same model as case 2 and case 3, but the Poisson ratio are different. We decrease it to the 0.2 and in case 4 and increase it to 0.3 in case 5. And we see that the low Poisson ratio increases the damage in case 4 and case 6. If you use a 0.2 for Poisson ratio, the damage is very high, and crack velocity is increasing with it. And the average velocities are given here, and we say that the higher level of damage are related with the greater crack propagation velocities. When the local damage is increasing, the velocity is increasing finally. And actually it shows the capability of the PD theory in fracture mechanics to simulate the crack propagation and the relation between the crack propagation and the damage levels. And when we compare the average velocities, the slowest one is case 5, and the velocity profile in the figure shows this. You see at the bottom of the figure, case 5, and the weakest model, the greatest crack velocity can be seen in the case 2. This is the wave propagation in case 5. at various time steps. The simulation, and these are the different times, and there is no applied force in the first time step, time 0, and then time 13 microsecond, the effect of the force can be seen here. The force can starts to apply here, and then there is a front wave in the 21 microsecond, but still no crack initiation yet, and it starts to at the next step on the 34 microseconds. The crack starts to propagate here. There is a small crack propagation here. At this point, there is no crack initiation yet. And then we have a reflection wave coming from the bottom of the body, and we can see this wave here. I draw a dashed line to see properly this reflection wave at the 52 microseconds. And after that point, the reflection waves mix with the compressional waves, and actually the kind of mode transition starts here. The transition between mode 1 fracture and mode 2 fracture, it starts the mixing of the reflection waves and the compressional waves. But the recording time is a little bit problem. Here I record the data about 4 microseconds. Maybe we need to record more smaller time intervals to see the better wave propagation. This is how to correct propagation. Okay, these are the relevant publications. As I said, the first one is under review now, the subject of this presentation, and the second one is in layout editing. It's accepted. It's from my PhD thesis. I tried to model the crack propagation in wire rope structures because wire ropes are kind of complex structures. They are circular and they have a helical path around between them, and their interactions are a little bit complex. And I have already talked about the last 2 papers. The first one, the last one is the homogeneous model. The third one is the FGM model. And this is another study. We tried to model the calving process of a glacier. A glacier can be brittle, and they can be modeled with the peridynamics. And the calving process, maybe you know that it's a part of the ablation mechanism of glaciers. When the glacier comes to the ocean, a huge part of the glacier from the terminus can separate from the main body and going into the ocean. And we use a linear elastic brittle model approach using peridynamics to model this calving process. And in the figure, you see these predefined cracks are the crevices, and they are naturally occurs on the top of the glaciers, and they are filled up with the water, and there are some water pressure, and in these simulations we take ice as homogeneous material. Actually it is not homogeneous material. The glacier is a kind of functional grade material or non-linear material, maybe another material model. We need to use it, we need to improve it. And because the physical properties in the ice are not identical in each layer, because the glaciers have some kind of layers. And on the other hand, there are some water pressures in the crevices. We need to add all of them, these effects in this model, but it's a kind of start. It's very preliminary study, and of course there are some other forces in the ocean, and maybe some kind of debris coming from the mountains or the bedrock layer because of the excavating effect of the glaciers. We need to improve the model, but it's just a start for us. Okay, thank you for all listening. I try to present a methodology to model of functional grade materials using peridynamics and tracking the crack velocity and the crack propagation. And here is my email. Thank you again.